I'm Eli.
This is Falco, Tyler, and Kenyon, and I'm Jack. And this is our group for the Equilibrium and Solubility video.
Solubility equilibrium is when the rate of the solid reactants turning into solvent products equals the rate of the solvent products turning back into solid reactants. This only occurs in saturated solutions. Okay, in this equation, the AgCl solid is turning into Ag plus ions and Cl minus ions. And then it's turning from Ag plus and Cl minus ions into AgCl solid. Stop it.
No.
The generic equilibrium expression can be written as Ksp equals your product A times your product B raised to the coefficient of the product. All right, and a good example of this with our AgCl, here's your Ksp equals Ag plus times Cl minus, and both of the coefficients are 1, so the exponents are just 1. And notice how there's no denominator like a normal equilibrium expression? This is because the reactants are normally the denominator, and the reactants in solubility equilibrium are a complete solid, which is the precipitate. So there's going to be no denominator because solid compounds aren't included in an equilibrium expression.
Go.
The next part of equilibrium and solubility is the common ion effect. So when we have a solution of AgCl, it dissociates into these ions, Ag plus and Cl minus. Now, if we want to add something to that, say NaCl, it dissociates into Na plus and Cl minus. Now, both of them have a Cl minus ion, which means that is our common ion. Now, in a saturated solution of AgCl, as much Cl minus is in it as it can be. Like, we can't dissolve any more of this into it to get more Cl minus. Hit the max. So when we add NaCl, we're trying to add more Cl minus ions where they can't go. This is going to cause a precipitate to form. According to Le Chatelier's principle, when we stress an equilibrium reaction, say we increase this, we stress this amount, the reaction is going to shift this way to the left, and it's going to form this solid. So we can see that here in this wonderful diagram made by Jack LaChance. So we got a solution of AgCl minus, or Ag and Cl, dissociated in solution. We add NaCl, now we got a bunch of ions, they're still floating in there. And since there are too many Cl's, the AgCl is going to precipitate out in the bottom as a solid.
Now we're going to compare Q to Ksp. So Q and Ksp are both found the same way. In like a question, you might be given one and you need to find the other, and then you're going to want to compare them to see which way the reaction shifts. So if Q is less than Ksp, then the reaction is going to shift right, meaning more products or ions are going to form. And if Q equals Ksp, that means you're at equilibrium. Nothing's going to shift anywhere. It's just going to keep going at the same rate. And if Q is greater than Ksp, it's going to shift left, which means more precipitate is going to form. And a good way to remember this is a good little trick here. You're going to have your Q, right? And then your Ksp. And whatever way your Pac-Man is facing, it's going to shift that way. I mean, come on. You get on the AP test and you know that trick? That's a 5. It's wraps. Let's go.
What does Ksp really mean? Ksp is the solubility of the substance that you got. So when the Ksp is over 1, it means that substance is very soluble. And when it's less than 1, it is far less soluble. So here we have two examples. We have this solution with a Ksp of 1.8 times 10 to the negative 10, and this one with a Ksp of 3.45 times 10 to the negative 11. This one is bigger by a fraction of 10, and this one is smaller. So that means that this one is more soluble because it's closer to 1. And for the last this is an MCQ about writing out the equilibrium expression for this compound mixed with water. And so to do that, we're going to have to take the molarity of our products over the molarity of our reactants. And since this is a solid one, we don't use that one. We just use the molarity of the water, which is 1. So we can do 1 over molarity And since this compound, we had 2 of them, we're gonna have to raise it to the 2nd power. So if this is our answer, we have to find the one which matches that, which would be C. Thank you for listening.
Okay. So, basically, what we're trying to make is a super saturated solution, but right now we're starting with a saturated solution of dissolved sugar. And it can't get super saturated on its own, so we're gonna have to add some heat. And what that's gonna do is allow more energy into the solution to break down more bonds, and boom.
Alright, so after the bonds are broken by adding heat, what we do is we like cool it back down and allow the bonds that were broken by the extra heat to like reform, and then that process forms rock candy, which is our precipitate. Yeah.
Because less bonds can be broken.
Okay, so I'm gonna be showing you guys how to write the balanced chemical equation for dissociation of that in water. So first we're gonna put H2O plus CuH2. This is gonna be the left side, the reaction. When we do the equilibrium sign. And we have to split this up into OH and Cu. And since OH is negative, we do OH minus, and we have 2 of them. Oh shit. And we ran out of space. Because we have 2 of them, we put a 2 in front, and it's negatively charged. And then for copper, we put it here, and it's positively. And since we have 2 negatives, we need 2 positives for copper. And then that's our balanced chemical equation. Thank you.
Go.
Okay. The next part of the question is to find the solubility in moles per liter of this copper hydroxide. Yeah. So we have it here in grams per 100 milliliter. So we have to change some of the units to get to our moles per liter. To start, we have to multiply everything by 1,000. Do some stoichiometry to cancel out the 100 milliliters. Write that
Mentioned.
like this. So, as we see, when we multiply this stuff together, we can cross multiply. So these will the milliliters will cancel each other out, and that would leave us with 1.72 times 10 to the negative fifth grams per liter. Now, this is 1/2 of the equation. We've got it in liters, but now we need to convert the grams to moles. We can do that using our molar mass of the copper hydroxide, which is 97.57 grams per mole.
And how do you get that molar mass?
We add all the pieces together. So we add the molar mass of the copper, the oxygen, and the hydrogen, and we add that all together, and that gives us 97.57 grams per mole. That we can set up like this. Then we divide that. It gives us 1.76 times 10 to the negative 7th gram, or not grams, moles per liter of solution that this is dissolved in. And that is how you calculate the solubility in moles per liter of copper hydroxide.
Now we're going to calculate our KSP value. So we have our equilibrium equation here. KSP equals the molarity of Cu times the molarity of OH minus to the 2nd power. So now we're just going to fill in our X values here, and we know X is 1.76 times 10 to the negative 7th, as we calculated in the last part of the FRQ. So this is just going to be X, so it's going to be X times And then this is actually going to be 2x because it's raised to the second power and it has a 2 as a coefficient right there. So it's going to be 2x, and then you're still to the second. As Mr. Ritchie says, it's double jeopardy. So, all right, so now we're going to combine our x and our 2x squared, and we're going to end up with 4x cubed. And then you're just going to plug in your x value, so it's 4 times 1.76 times 10 to the negative 7th, which again is our molarity from our last question, and that's cubed. And then you just do the math. All right, so you're going to do your exponent, and then you're going to multiply by 4. And in this situation, we got 2.18 times 10 to the negative 20th equals our KSP value.
You did that in your head.